All right. Welcome to the last session, and I think the last talk, right? Because Hank Coffee isn't going to make it today. So our last speaker, we're lucky to have Rachel Mandelbaum from the physics department, who's going to tell us about some future challenges.
Hi, everyone. It's a pleasure to be here. I'm going to talk about things related to analysis of data from large sky surveys, and I will be doing my best to make it accessible, but I hope people will ask if you have any questions throughout. So I'm going to start by talking about some of the science I do and some interesting challenges where statistical methodology can help, but also talk a little bit more broadly about the science people do using data from large sky surveys, including defining what is a sky survey. I will get there. But I'm first going to just start with like my science, which is called weak gravitational lensing. So I'll tell you what that is and why you should care about it. So this pie chart shows our current best understanding of the contents of the universe. So it's a little awkward in that there's this little yellow slice of pie that's like 5%. That's the ordinary matter. So when you hear matter and energy and you think, okay, like matter, right? Light rays from the sun, when you hear energy, that's only 5% of the current energy density of the universe to the best of our knowledge. The next biggest slice of the pie is dark matter. There's a lot more of that. And that is something that is revealed through its gravitational influence on other matter, but it doesn't interact in the ways that we're used to, like we can't see it. Then the biggest slice of pie is this thing called dark energy, or you sometimes hear cosmological constant, which is like a special case of dark energy. And it's something that causes the expansion rate of the universe to accelerate. So we don't actually have a precise physical model for what it is. I mean, there are physical models, but we don't know which is the correct one. But the basic idea is that normal matter, if the universe just had normal matter and dark matter, then the expansion of the universe would be decelerating. It would be slowing down because of the gravitational influence of all of that stuff. But it's not. The expansion of the universe is accelerating, so something weird is going on, and that's the biggest slice of the pie. And since, only 5% of the pie is ordinary matter, and we kind of want to understand what the other things are, we need some kind of way to probe those other things, and weak lensing is my preferred way to do that. Okay, so I said weak gravitational lensing. So first, just what is gravitational lensing? It's essentially the deflection of light rays from very distant objects, distant galaxies and quasars, by other matter on its way to us. And you may have seen pictures like this with this, blue arc that looks pretty distinctive and obvious. And that's essentially the image of a galaxy that's directly behind this other galaxy, such that the light rays are actually following multiple different paths around it. And so that is essentially telling us about the distribution of matter, including dark matter in this galaxy nearby. And the thing about it, though, is it depends on this serendipitous effect that there's one galaxy pretty much directly behind another galaxy. So it's easy to see, which is nice. Like this clearly looks weird, like something's happening there. We can tell it's a strong lens, but it depends on this, alignment effect. And so it's a rare phenomenon. So, and that's not what I measure at all, but it's easy to show a picture of. So I start there. So I measure what's called weak lensing. So weak lensing is still deflection of light by mass, but in the limit that the deflection is very small and you just get a single distorted image. So you can't look at it and say a single very mildly distorted image. So you can't look at it and say this galaxy was weakly lensed. But the nice thing about it, though, is that it happens everywhere. Every single galaxy we see on the sky has passed by some clumps of, normal matter or dark matter or whatever, and been weakly lensed. So if we want to measure weak lensing, we can use every single galaxy that we measure on the sky. And so what it does is if you imagine having a distant set of galaxies that are like circles, perfect circles on the sky, and you ask, what would happen to the circles? How would we observe them? What would they look like if they were weakly lensed by some matter that, as that it passed by on its way to us? And you would get these distorted kind of ellipse things that have these coherent patterns in them, right? They're no longer circular, and the galaxies that are near each other are kind of smeared out. The shapes are smeared out in the same way because they're passing by the same objects. And so we want to look for coherent patterns in the galaxy shapes. The fundamental assumption being that if there was no lensing, then the galaxy shapes would just, there'd be no physics setting it. So in this case, they would be circular because that's our starting point. But more generally, they should be randomly oriented. They shouldn't be coherently aligned, which is an assumption that's slightly wrong for other reasons, but let's leave it there. And so someone like me who works on this a lot can look at this and immediately say, there's a lens here because things are, smeared tangentially around it, and we can pick out where all the masses are, but it doesn't really matter. The point is we're just looking for those patterns in the galaxy shapes. And of course, galaxies are not round, but that's still okay. If the galaxies have some random component to their shape and then a small additional distortion due to lensing, the random component in their shape should average out. It's not coherently aligned with the other nearby galaxies. And so if you average over enough galaxies, you can still measure this effect. So the way to think about it is, we have galaxy catalogs. They might have tens of millions, hundreds of millions of galaxies, eventually billions with upcoming surveys. And we're looking to measure these tiny coherent shape distortions, percent level or less, underneath, 30% level ellipticities that we have to average down. So that's a statistical error. And we also have to model and remove any non-lensing effects that might cause comparable coherent distortions in the galaxy shapes. So that would be a source of systematic error. And if we do that, we get a lot of very cool science. So one thing you might have seen before is people saying, we've made a map of the distribution of dark matter, something like this, where the bright peaks are like there's more matter and the dark areas are where there's less matter. So learning where is the matter distributed in the universe. So one thing we can do is we can correlate that with the positions of the galaxies we see and ask questions like, how do the visible parts of galaxies we see relate to the dark matter that is surrounding them? Because galaxies have formed essentially inside of clumps where there's a lot of dark matter. Another thing we can do is learn about how cosmic structure has grown over time. So in the early universe, this is a simulation box shown at 3 different times. In the early universe, the matter density was very close to smooth, just tiny inhomogeneities, but gravity causes those to attract other matter, and eventually things gravitationally collapse, and you get this very structured kind of cosmic web thing. And this cosmic web is then lensing. So we can use lensing to measure how cosmic structure has grown over time, which goes back to our pie chart. It tells us about, especially about this dark energy stuff, because it accelerates the expansion of the universe and slows down the growth of cosmic structure. So weak lensing tells us a lot about a lot of cool things that we really want to know about in cosmology and astrophysics. Okay, so then we get to large sky surveys. So this is kind of busy. I'll get there in a second. But first, just to say what's a sky survey. It's when a bunch of people say, let's use this telescope to look at some area of the sky systematically over some period of time, instead of like you write a proposal and you look for one day at this thing and someone else writes a proposal and looks for one day at this other thing, completely different goals, right? I have a goal. I want to look at some volume of the universe for some period of time to learn about cosmology. So that's a sky survey, and sky surveys have been going on for decades. And so the names written on this plot are just names of a bunch of sky surveys. And so the horizontal axis is the area of the survey going all the way from a tiny patch of sky to the entire visible sky. And the vertical axis is essentially like how faint are the galaxies that it can see. Can only see bright galaxies at the bottom, can see very faint galaxies at the top. So the main point is that the most powerful imaging surveys are in the upper right corner, the ones that can see a large area of the sky and also very faint galaxies. Then you're seeing kind of the largest possible volume of the universe. And so the march of progress in the past 2 decades has been along these arrows pointing to the upper right. The surveys have been gathering more and more data. The data have become more powerful. They've also become more complex. They've started to include more things, images of the sky, spectra, time series data, and more. And so what we're leading up to is the Vera Rubin Observatory's Legacy Survey of Space and Time, which will be starting this calendar year. So that's the LSST. It's a 10-year survey that's going to look at every point on the visible southern sky approximately 1,000 times during a 10-year period. So building up a time series view of the southern part of the sky. And it was optimized for a number of different science cases. Some are in cosmology, like the stuff I just mentioned, the dark energy, dark matter, but also understanding our solar system. Like, can we find planet 9? Do we understand the distribution of, asteroids and near-Earth objects and other things like that? And also stellar astrophysics. How are stars born and how do they die? And learning about all kinds of new stellar populations that we, haven't seen before. The challenge is this is going to be an enormously large data set. It's essentially like a, multiple gigapixel camera that is going to take a new image every 30 seconds per night for 10 years. So a lot of data. And it's going to be looking at, around 40 billion stars and galaxies, 30 trillion observations. That means because at each point it's coming back close to 1,000 times, more like 900 times. So that's why 40 billion and then 30 trillion. 500 petabytes of images. So there are a lot of challenges in just, pulling information out of this very high volume and complicated data set. Sorry, I forgot that was animated. Anyway, that's just a picture. That is just a picture of the telescope now. Okay, so I wanted to talk a little bit about my particular science, the weak lensing science, and areas where statistical methods can really help us. So I mentioned earlier, that there are some statistical uncertainties. And obviously we want to extract as much information as we can. And our current analysis methods are not really optimal. And there are also systematic uncertainties, data analysis challenges where maybe our current modeling and mitigation approaches are not enough. Things like estimating the distances to galaxies. So I put stars next to these because these two are the things I'm going to talk with in a bit more detail, but I want to emphasize there are a lot of other interesting places where help is needed in analysis of these survey data sets. Okay, so before I explain what this plot is, I just want to say, sort of as a basic point, when people try to measure lensing, the weak lensing effect, they generally measure what are called 2-point correlation functions. So just if I have a galaxy shape here, like how correlated is it with other galaxy shapes at a particular distance away on the sky? So just it's a single, function of how separated are they? And it's a 2-point correlation function. We only ever consider 2 points at once. And so some of you may be aware, if you have a Gaussian random field, then that 2-point correlation is fully sufficient to characterize the field. That's all the information you need. But if you have a non-Gaussian field, then there is additional information out there. And so the point of this is essentially to show you that the weak lensing field, that we call it shear, that's the shape distortion. The weak lensing shear field is a non-Gaussian field. We've been using 2-point statistics, therefore we are throwing away some information. And it's worth considering, can we do more? So this thing that I'm going to be showing a lot of kappa is convergence. The way you should just think about it is we take the density field along the line of sight and we just project it. So it's like a surface density, mass per unit area. We normalize it by some reference surface density, and we subtract the mean so that we get something that has now a zero mean quantity. So that's what this kappa thing is. Excuse me. And so these three images are basically, if you take a single reference power spectrum and generate random fields with different one-point distributions, like a Gaussian random field on the left, or these are other histograms of kappa. One is a log normal. One called Takahashi is named after a set of simulations by someone named Takahashi. And so you can see that the 1D histograms look different. The Gaussian one looks kind of like what you would expect. The other ones, so the Takahashi one, this is a real cosmological simulation. So we expect it to be closer to reality. And you can see that the distribution has a narrower core, right? But then also larger tails. And you can kind of see that visually in these, right? Like if you just say, can I find these tails? Well, there are more bright spots in the log normal and Takahashi than in the Gaussian one. So you can even just see by eye that these fields look different. And so an obvious question then is, could I measure the lensing shear field like in little pixels on the sky and treat it like a field and try to model that instead of just looking at 2-point correlations? And so that's something that a student named Alan Zhao did. And the short answer is yes, you can do that. So he employed a Bayesian hierarchical inference approach. And so one of his key takeaways was just that in that process, model misspecification biases can really matter, and they can lead to biases either in what you learn about cosmology or in your uncertainties that you infer. And so in this particular example, the idea is that he took data sets that had a Gaussian, log normal, and Takahashi distribution, and then he modeled all of them as a Gaussian distribution, right? So on the left, and he just asked, what's the amplitude of the power spectrum? And on the left, the model matches the data, and not surprisingly, so the points are essentially on the right answer. And the bottom essentially says that the probability distributions well match the real ones. But then on the right, where the data don't match this Gaussian model, so in this particular case, it was kind of interesting to us and not obvious this would happen. We found that the power spectrum amplitudes we inferred were actually unbiased, but the uncertainties were really, really off. And so we did some digging to understand why that's the case, and also, of course, considered the reverse direction. Reality is more like that, you could imagine saying, oh, well, we know it's not a Gaussian model. We're going to try to use one of the other ones, but what if the one I'm using is not quite right? So we did some exploration of this and found an approach that we think could work for current survey data sets. It's sort of accurate at the 2% level. So good enough for current data, not good enough for future surveys like LSST in full. And so there's room for further development there to understand and mitigate the model misspecification biases. And so, in fact, a student sitting in this room, right over there, is working on some of the future work. We're going to apply this to real data. We also need to be able to model some additional systematics that were not in the mock catalogs we used for some initial tests. And the basic idea is that, cosmologists have spent literally 2 decades using 2-point correlation functions to analyze weak lensing. We've built up a very good understanding for how different systematics enter the 2-point functions. So we have some additional work to do to understand how to model them in a field level analysis. Okay. The other challenge that I wanted to mention was redshift estimation. So redshift, this is essentially a recession velocity due to the expansion of the universe. And it's a proxy that we use for the distance to the galaxies, which is something we need to know if we want to interpret the weak lensing distortions in terms of cosmology. So the basic idea is if we could measure galaxy spectra, right, the light as a function of wavelength, like these curves, then when a galaxy is redshifted, these curves move to the right, and we would measure that and we'd say, okay, like these dips, these should happen at certain wavelengths. They're happening at other wavelengths. That tells me about the redshift. But we don't get the spectra. We're only getting images averaged over very broad wavelength ranges showed here. And so we don't have enough information to precisely measure a redshift. We have to try to infer it from just a few numbers that you could think of as extremely coarse spectra, so coarse that they don't contain, the information that we can easily see by eye in where these dips are located. So we call those redshift estimates from imaging data photometric redshifts. And those are often, that challenge is often resolved with machine learning. If we have a training data set where we do know the spectra, like a small sample of data that's representative of our imaging data with real redshift estimates, then we could try to, use that to build a model for redshift from the imaging data. And so this plot shows kind of an example of that in a very simple setting where the true redshift is the vertical axis, the horizontal axis is the photometric redshift. And you can see, okay, like it does pretty well. There's some outlier regions, but a lot of galaxies on the one-to-one line. So that seemed to work okay-ish. The challenge being that we don't usually have a representative training set with spectra, so it's kind of a problem. So the nice thing for weak lensing is we don't actually care about the redshift of any one individual galaxy. What we care about is the redshift distribution of the ensemble. Like on average, how far away are the galaxies, not how far away is that one galaxy and that other one galaxy. And so we can try to statistically infer the distribution of redshifts for the ensemble rather than information about each galaxy. The way we do that is by correlating it with a sample of galaxies that have known redshifts. So if galaxy positions on the sky should not be correlated with each other unless they're in the same, part of the matter distribution, such that, gravity has caused them to be pulled closer together. So we can essentially cross-correlate to pick out, okay, I have a reference sample, which, and are the galaxies that I actually care about, like near these in terms of distance from us or not. And we can build up a statistical picture of the redshift distribution. The basic idea is, so imagine you have this distribution of galaxies shown in the black, and imagine you had just a bunch of reference redshifts, like this comb distribution. So just a bunch of redshifts at redshift 0.1 and 0.2 and so on. And you could cross-correlate them. The nice thing is that this reference sample doesn't have to be representative. It needs to cover the full redshift range, but it's okay if it has a completely different distribution. And it works even if the measurements of the light for the galaxies is affected by other nearby galaxies. So there have been a few Bayesian hierarchical implementations of this. But one thing that my group has been trying to do is include other information, right? We want to use the clustering information, but we do have photometric redshifts that aren't terrible. So it'd be good to be able to combine the two at the likelihood level. And so we've been working on doing that. And I'm just jumping to a result given the timing. So this is an example from an imaging survey where we've made 4 sort of rough bins in redshift and tried to infer the redshift distribution for each one of them, using cross correlations with where possible and using photometric redshifts alone otherwise. And you can see, so for 3 of the distributions, we have these points. Those are from clustering. We don't have that for the 4th, and that's because we didn't have reference redshifts at high redshift. Our reference sample only went up to redshift 1.2, and then it stopped, and so we couldn't keep going. So bottom line is, this is promising. And our 2 challenges coming out of this were, 1, get a more complete reference sample, like need more data. That's not the interesting statistical challenge. The interesting statistical challenge, though, is that there are some systematic uncertainties and biases in the photometric redshifts that we need to model and remove. And that's something that is still kind of work in progress to do properly. So I'm going to close with just a very few minutes on something that is supporting this statistical analysis rather than being the actual statistical analysis. And that is about the software infrastructure to apply statistical analysis to survey data sets, working at scale. So something like LSST with tens of billions of objects. So if you were here in the morning session and you heard the lightning talk by Melissa about link frameworks and the software infrastructure, I'm talking about the exact same thing. But in the morning, you heard the engineer side, and now you're hearing the Astra side. So you're getting the true link frameworks experience, hearing from both components of the team. Okay, so this team is led by CMU, University of Washington, and the LSST Discovery Alliance. And the goal of the team is to provide the software infrastructure that makes it possible for scientists to pull the science out of large and complex data sets like the Rubin Observatory LSST. And enabling machine learning and statistical applications is, a strong interest of ours. And so I wanted to briefly mention two areas for software development where we've been trying to do that. So one is HIRAX, which I think Melissa showed the exact same slide. Right. So HIRAX is essentially meant to do all the homework around your machine learning algorithm. So maybe you want to run a machine learning classifier on a set of image postage stamps or a time series data for time varying objects. You also have to do a whole bunch of bookkeeping around that. Like maybe you want to run it, in parallel on a supercomputer, or you need to acquire the data from it lives somewhere else, right? And organize the data, and you need to monitor the different runs and analyze the outputs and so on. And so the idea is that HIRAX does that stuff so that you can focus just on developing your machine learning algorithm that you want to apply. And in the interest of time, I won't talk through that, but if you're interested, I'm happy to talk with anyone after about HIRAX. I also wanted to highlight spatial analysis software, and this, I think, Melissa showed in some form as well. Right, so this is basically, you should think of HANS as essentially an efficient storage format for data that lives, across the sky and potentially has, different densities at different points on the sky, and so would benefit from storage in different ways. And LSDB is a framework for parallel distributed computation over the spatial data. So if you imagine having a catalog of tens of billion of detections with LSST and, of order a billion detections from Gaia, and you want to cross-match those and then analyze the light curves for the things you cross-matched, that's a pretty non-trivial computation. And LSDB is meant to help you do that efficiently. And it also includes what's called nested pandas to handle time series in a very kind of natural way. So it's not just the spatial data, but also the time series. And so we've demonstrated LSDB in a number of different contexts using Rubin Data Preview 1, so early commissioning data, and various simulated data sets. An example I'm going to highlight in the middle here was an analysis of Rubin Data Preview 1 to identify a number of interesting objects that had time variability. So in this particular case, objects with this kind of periodic variation. So just to close, I hope I convinced you that weak lensing is an important cosmological probe that's going to be carried out with data sets that are just coming online. Statistical approaches can help us get better information, out of the data, as long as we're careful about, model misspecification, biases, and the uncertainties. And I want to emphasize that I just looked at my narrow scientific corner of these surveys, but there are like many other places where scientific discovery could be, improved or even just made possible in the first place through novel statistical approaches to the data. And if you want to do that with large data sets, improved data infrastructure will be essential. And so come talk to Link Frameworks if you want to know more about that. Thank you.